All right, so welcome everyone to the Physics Department Colloquium. I'm very happy and honored to be able to introduce to you Professor Howard Wiseman, who is the director of the Center for Quantum Dynamics at Griffith University. Howard did his PhD with Gerald Milburn, a name that's well known to many of you, at the University of Queensland, before going on to do a postdoc with Dan Walls in Auckland, and then returning to Australia, where he's been ever since in his very illustrious career. He's won numerous awards, going back to the award for the best PhD thesis in Australia. He's a fellow of the American Physical Society, the Optical Society of America, as well as the Australian Academy of Sciences. I'm even more impressed by the fact I only learned recently that he won a summer vacation scholarship in theoretical physics, given that I always thought theoretical physics was a vacation in itself. I wasn't sure what the point was, but I'm sure it was a very prestigious honor. He's also very well known for his two books, or at least one of them, one with Milburn on quantum measurement and quantum control from 2010, which is sort of one of the Bibles of the field, as well as a so far less well-known in our field book called Then Arthur Thought, but which many of you ought to look up if you're interested in Arthurian history and legend. And over his decades in the fields of quantum optics, quantum feedback control, and the foundations of quantum mechanics, has really made innumerable contributions in a variety of different directions. I think you'll be very interested in the latest theory and experiment that he's participated in and has been kind enough to get up in the middle of the Australian night to tell us about. So with no more further ado, over to you, Howard.
Thank you, Ephraim. Thank you for the very kind introduction. And it's indeed morning now in Australia, even by any standards. So I put this page up just for people's amusement to read while Ephraim was talking, or whatever, while you were waiting for me to start. I thought about, I hope it's a surprise for Ephraim. I thought about sending it, when he invited me or suggested I give a seminar on October the 1st, of replying and saying, oh no, October the 1st is too late. But anyway, but that would have spoiled the surprise that I wouldn't be able to then use it again in here. So if you did manage to read the quote, you will see that it seems eerily relevant for something in 1966 for the topic that I will be talking about. But we'll get to that. It's not essential for you to have read that, but I do think the book is rather interesting. Okay, so oops, oh dear, how do I advance? Oh dear, that's because I'm on this silly text thing on. How do I get rid of that?
There should be an X on a little annotate box that has.
Maybe that's what I want to do. And now if I click here, yes, there we go. Okay, sorry. So the actual title slide, can a qubit be your friend? Why experimental metaphysics needs a quantum computer. So this is work, as Ephraim said, I'm at the Center for Quantum Dynamics in Griffith University, which is here in Brisbane and indeed on the Gold Coast in Australia, but I'm in Brisbane. And because it has something to do with the quantum computer, this is also part of the Center for Quantum Computation and Communication Technology, which is an Australia-wide, well, at least several cities in Australia, in the center. And we actually, yes, some of you may have heard that we now have a link with John Martinez having relocated to Sydney to join a company which is associated with our center. So that was pretty exciting news for us. But to go on to the topic of today, yes, so I will be talking to give yet another title. So you had a title and a subtitle, and now here we have another title, which is the actual title of the paper, which I will be talking about. So this is work with several authors, several co-authors. So it's both theory and experiment. And so the experiment was done in Jeff Pride's lab. He's in the Center for Quantum Dynamics also at Griffith. The corresponding authors, I should point out, are Eric Cavalcanti and Nora Tischler. Outside of Griffith, so we have Kokwe Bong and Anibal Itreras Lacon. the PhD students. Fazad was a postdoc. Yongcheng is the only non-Griffith author here. Yongcheng Lang at National Cheng Kuk University in Taiwan. I've got that right. Okay, and this is a little bit of artwork which we had commissioned to celebrate this. So I will be talking about this paper, but then in the second half of the talk, and maybe I'll have a little pause between the first and the second half, I'm going to go on into a more speculative direction, even more speculative direction, you might say, a bit beyond what is in this published paper. And so that's just a warning that this is still work in progress, which, yes, hopefully will come out sometime on the archive at least. A little bit of more commentary on the main paper, but exactly who the authors will be apart from me is still being worked out. Okay. So yes, so this was obviously a non-commissioned artwork down here below, but the photo is used with permission from IBM. It's IBM just because they were the ones who had a photo that I could find online of somebody looking sort of longingly at a quantum computer. And although it looks, it may look facetious, as we'll see, it's making a genuine point about the possibility which would be required of actually having a relationship with a quantum computer. Okay, so that's a foretaste of what's to come. So the big chunks of the talk are an introduction, then the discussion about the new paper, and then beyond that, as I said, will be the part which, is beyond that. So maybe I will just jump straight into the introduction. So to begin with a motivation for this work, we can ask, so many people, of course, are interested in building quantum computers, but we can ask, why are we building them? For whom are we building a quantum computer? And there are many potential answers to this question in no particular order. Here are some which have been proposed. This one is a little bit different, obviously, from the ones beforehand, and arguably has already been realized. But I won't go into that, but it's not really the topic of the talk. Well, it's definitely not the topic of the talk. Here's an interesting one. But what I'm going to talk about here is one which hasn't really been talked about very much, which I think is building a quantum computer for philosophers to advance experimental metaphysics. Okay, so I'm sure everybody here knows what an experiment is, but maybe not everybody knows what metaphysics is. So here's just a dictionary definition. It's a branch of philosophy that deals with basically the most fundamental things that we can imagine. So according to this definition, first principles of things, including abstract concepts such as being, knowing, identity, time, and space. So metaphysics has a bit of a bad reputation in science, at least ever since David Hume. He said this: if we take in our hand any volume of divinity or school metaphysics, for instance, let us ask, does it contain any abstract reasoning concerning quantity or number? No. Does it contain any experimental reasoning concerning matter of fact and existence? No. Commit it then to the flames, for it can contain nothing but sophistry and illusion. Okay, so what I'm going to talk about, experimental metaphysics, is notable precisely for doing what David Hume says is not in metaphysics. In other words, it does contain abstract reasoning concerning quantity or number, and it does contain experimental reasoning concerning matter of fact and existence. So I'm hoping to convince you that it is a suitable topic for discussion in a science, indeed physics colloquium. So the term experimental metaphysics goes back more than 30 years. It was introduced by this philosopher, Abner Shimoni, late philosopher, in this book in 1987. And indeed, as you see, was even the title of a conference held 30 years on from the book where this was first mentioned. So as you see from the title of the book where it was introduced, the subtitle of the book, Reflections on Bell's Theorem, shows that there is a special role for this thing called Bell's Theorem in experimental metaphysics. And indeed there is. Bell's theorem is really the first theorem of experimental metaphysics. And so it's really crucial for understanding the type of result that I'm going to be talking about. And more than that, actually, it actually underlies the result that I'll be telling you about. So we need to start by understanding a bit about Bell's theorem. So I know that, so for some of the people listening, this will probably be very familiar, but for others, it may be the first time. For the latter, I apologize that he will be going rather fast, but hopefully you may get something from it. Okay, so Bell's theorem dates to 1964. Introduced by John Bell in this paper called On the Einstein-Podolsky-Rosen Paradox. And I think that actually his words in this paper will serve perfectly well to state what the result that he proved in 1964. And it's this: the statistical predictions of quantum mechanics. And you'll see that throughout this talk, I will try to at least consistently use this brown color when talking about things which are experimental, things which can be observed, things which are empirical, and not that color for things which could be metaphysical assumptions, as we'll get to in just a second. Okay, so the statistical predictions of quantum mechanics, that's experimental, are incompatible with separable predetermination. That is, in any theory in which parameters determine the results of individual measurements, there must be a mechanism whereby the setting of one measurement device can influence the reading of another instrument, however remote. Okay, so this is the foundations of, well, the field of quantum foundations to a large extent since then, an incredibly important theorem, and also very important these days in much of quantum information. And of course, Bell being having lent his name to the Bell Prize, which Ephraim and others have created for the community. Okay. So, right, so yes, so Bell in 1964 talked about the statistical predictions of quantum mechanics. He didn't talk about the actual observations that had been recorded for quantum experiments, because in 1964, no such experiments had been performed. But where are we now? Well, as many of you probably know, in 2050, I mean, there's been a very long process since 1964 of doing experiments to test whether these statistical predictions that Bell is talking about here actually hold. And they culminated, many would agree, in 2015 with 3 experiments which demonstrated in a loophole-free way exactly these predictions that Bell was talking about. But rather than put up any of those experimental papers in the interest of strict neutrality between the 3 teams, I'm putting up a 2015 paper by somebody else, just a commentary saying that the implications were death by experiment for local realism. Okay, so that was, I think, a pretty important day in quantum foundations, or year, when we had this happen. But you see that there's a little bit of a mismatch between the words used in this title and the words which Bell used. The words in this title were obviously taken from the paper, which this was particularly reporting on. Right, what exactly is going on here? We have the word local here, but Bell used the word separable and the phrase that no setting can influence the readout, however remote. And then we have the word realism, but Bell didn't use the word realism. He used the word predetermination and talked about something determining something else. So exactly what are the metaphysical assumptions that are leading to a contradiction with experiment? Okay, what conjunction of assumptions is actually ruled out by Bell's theorem and by the experiment? So there are many different ways to formulate these assumptions, but for the purpose of this talk, the most convenient way is very closely related to what Bell originally did, but being a bit more explicit. So we can say, in other words, the Bell experiments rule out the conjunction of these three metaphysical assumptions. The first one hasn't been mentioned at all so far, but is actually important. Absoluteness of observation. An observation is a real single event and not relative to anything or anyone. And you might be wondering what else could it possibly be, but if you're in a field of quantum foundations, then you'd be aware that there are whole communities of people who doubt or deny number one. Okay, number two, predetermination of observable events. So I'm not going to read the description of that. The idea of the way I've presented that description is that it's not terribly elegant, and I don't want you to concentrate on that because we're going to get rid of that soon enough anyway. But this is essentially Bell's assumption and Bell's words, but put in some rigorous language that allows us to absolutely rigorously prove the theorem. Okay, and number three is not exactly the word that Bell uses. It's not the word that many people use at all, but it's the simplest assumption to use in this context. And it's what I'm calling local action. Okay, so this is an important one to go through. So local action says that any free choice, X, say, made in a manner appropriate for a randomized experiment is, for the purpose of that experiment, correlated only with events in its future light cone. Okay, so in other words, only with other events that could have been influenced by a light signal traveling outwards from that event, or something slower than a light signal. Okay, so this is sort of where relativity comes into the picture. So just a note, so this is not the same, not exactly the same as either local causality or locality, if you're familiar with those terms. And also, if you're wondering about where's the freedom of choice, well, okay, essentially that this wraps up the locality assumption and a freedom of choice or no superdeterminism assumption all into one neat and elegant package. And that's all we need for the purpose of Bell's theorem here, and all which we need for the theorem which I'll tell you about. Okay, so that's the review of Bell's theorem so far. The other crucial ingredient into the work that, oh no, it's not the end of that, because I'm going to be a bit kinder to you and actually explain to you how that pans out for an experiment. So this is these here were very abstract, wordy looking things. Many people will be more familiar with, stating Bell's assumptions in terms of equations. And so for that purpose, the specific setting that we use in a typical Bell scenario is what's called a bipartite setting. So this is a space-time diagram with time going up. So I have one lab over here, which we call Alice's lab, another lab over here, which is Bob's lab. Alice has a free setting choice, X, Bob has a free setting choice, Y. And then on the basis of that, they get their outcomes A and B. Okay, at some earlier time, which being as general as possible could just mean at some way of cutting up space and time, we have a space-like hypersurface here. There could be some other things in the world that influence these outcomes, okay? And we just call them lambda and imagine that they're distributed anywhere we like. They could be even just imagined to be non-locally specified everywhere on this space-like hypersurface. It doesn't actually matter. Okay, so then the predetermination assumption says that given everything that happens before, these outcomes are determined. Okay, the probabilities for outcome A for any value of these x, y, lambdas, and when I say before, I mean before in the most general sense, conceivable, like not in a relativistic sense, but so the probability of A given lambda x and y is either 0 or 1. In other words, there's only one possible A if I specify all these pre-parameters, which could potentially, you might think, influence A. Okay, and likewise with B. Okay, and so I don't have to include B here because, well, B is also just determined by all of those things. Okay, so that's predetermination. Local action is where the speed of light and whatnot comes in. So that's where these diagonal lines which I've drawn, these are representing light cones. That's where that comes in, and the implication of that is that, in fact, so that the probability of A here can only be influenced by things in its past light cone. So I can say that the probability of A given lambdas x and y is in fact only the probability of A given lambda and x, because y is space-like separated from A, and so could not. It's a free choice which can be assumed to be independent of things outside its future light cone over here. I hope you're seeing the mouse, which means in particular it's going to be statistically independent of this A over here. And likewise for B, and also another consequence is this sometimes what's called a separate assumption of freedom of choice, which would be that the probabilities of the lambdas are independent of X and Y. Okay, I think these are all perfectly reasonable. I think it's reasonable to wrap them all up as one conceptual metaphysical assumption, which we're calling local action. Okay, so the point is so I haven't mentioned assumption 1 here. So assumption 1 is just that these things really exist. Okay, A exists, B exists, X and Y exist. Okay, so it makes sense to write down, talk about joint probabilities of these events because they all really exist in the same universe, so to speak. Okay. And as I said, you might think that's uncontroversial, and I'm happy enough to go with that at the moment, but that is obviously an assumption that we make in Bell's theorem, that it just means something to write down this probability, and that when we measure that experimentally, we are in fact measuring the probability that these events really happened, and not something else which we could talk about if somebody wants to ask at some point. Okay. Right, so now, as I said, yes, we get to the other key ingredient in the paper that I will be mainly concentrating on, and that dates to around about the same time as Bell's experiment, but it's from another experiment using Wigner. And so this is basically musing on the quantum measurement problem. That's what QMP stands for here. So it was in an essay called Remarks on the Mind-Body Question. And here's an excerpt. I think, yeah, again, that the actual words from the 1960s can stand for themselves to explain what's going on. So Wigner wrote, "It is natural to ask about the situation if one does not make an observation oneself, but lets someone else carry it out. What is the wave function if my friend looked at the quantum object? The answer is that one could only attribute a wave function to the joint system of friend plus object, and described by this equation here. So psi and chi refer to the quantum object and the friend, and here we have a superposition of two possibilities if the system, say, was a spin with two possible outcomes. And he says that this wave function follows from the linearity of Schrodinger's equation. Then he goes on, "This appears absurd because it implies that my friend was in a state of suspended animation, before he answered my question about what he saw. So he's saying this is the state before I then go and, so I'll take it for granted that if I make a measurement, I collapse the wave function into one of these definite eigenstates. But according to quantum mechanics, according to the linearity of Schrodinger's equation, my friend is just a physical system, and so the superposition will grow to include the friend and won't actually collapse until I get involved. So then he goes on and makes this this famous remark, for which this essay is known. It follows that Schrodinger's equation cannot be linear if it is accepted that my friend has the same types of impressions and sensations as I. Okay? So he's actually, yes, so he's saying that not only that this appears absurd, he's saying that in his point of view, it is absurd, that it just simply cannot be the case that Schrodinger's equation applies to to a sentient observer, to a friend, that in fact the collapse must have happened at the level of the friend before I got involved at all. Okay, so those, as I said, are the two ingredients, but putting them together was not our idea. It actually, it probably occurred to a few people, and some of you may be aware of other papers in this area that I'm not going to mention. But the one paper that was a particular inspiration for us was this one by Czeslaw Bruckner from Vienna, which was published in 2018. He called it a NoGo Theorem for observing independent facts. But the basic idea was to incorporate Wigner's friends into a Bell experiment. So combine these two ideas to get something new. And the motivation was to get rid of that predetermination assumption, the assumption that was rather ugly to formulate, and moreover is the one that, I didn't say this, but probably the one that people would think is the obvious one to question, to throw out in the world, that it seems like, okay, well, I'll give up predetermination. That's something I can live with. Okay, so to get something more interesting, the idea, as I said, is to get rid of that metaphysical assumption and replace it by something which is less easy to get rid of, as Wigner recognized, which was something to do with friends' observations. Okay, so in this case, if the experiment actually succeeded, it would require, contrary to Wigner, that the friends actually are in superpositions and do not collapse the wave function. And we'll get later to what that could actually mean. Okay, so this was a very nice paper. However, the ideas behind it were nice, but in our opinion, the formalization of the assumptions were done in an unreasonable way. And if one replaced the formalization that Bruckner used by a more reasonable formalization, then his proof just didn't go through. But the good news, and this is where our paper comes in, is that there is, with a reasonable formulation of the assumptions, a new proof. And so there is a new theorem of experimental metaphysics, which I'll now tell you about. Okay, so this is this theorem that we have here. So as we called it a strong no-go theorem on Wigner's friends paradox, or at least that's the title that we were forced to go with. Okay, so what is this theorem? It's a conjunction of three assumptions, leads to a contradiction. And one of these assumptions, well, okay, we'll get there. Only two of these are metaphysical. In the presentation I'm giving here, the paper is slightly different, but I'm not going to go into that. Okay, here we go. Contradiction. So one, absolute of observation. So this is exactly the assumption that we talked about before, that we need for Bell's theorem as well, even though it's usually done implicit, said assumed. Implicitly, an observation is a real single event and not relative to anything or anyone. So that's the same. Number three is the same as number three before. Local action, any free choice, blah, 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 is correlated only with events in its future light cone. But we have now no predetermination. That assumption is gone. The assumption which we have, and you see from its color that this is not a metaphysical assumption. This is an assumption that can be decided by experiment. is something which I've called here a bit facetiously superpowers. Okay, again, this is not actually in the paper, but I think it better reflects the nature of the assumption we're making here. It's that a super observer, and so I call it superpowers because super observer is a term sometimes used in this context. So Wigner is a super observer, an observer of an observer. A super observer, such as Wigner, can perform arbitrary quantum operations on an observer, the friend, and the friend's environment. Okay, so that's a very strong assumption, but as I said, not metaphysical, something which we could actually, for a given Wigner and a given friend, more or less decide experimentally whether it's true or not. Okay, so how does this work? So we have two boxes with two parties in it, Charlie and Debbie. They are going to do, and an entangled pair. So this is just the, I suppose I'd never actually mentioned that in Bell experiments. How do you violate these Bell inequalities is by using entangled particles. So there you go. In case you didn't know. But so this is what's going on here. We have an entangled pair of particles shared between these two labs. And Charlie and Debbie, make a measurement on that particle in some basis, get an outcome. And then let's just concentrate on one of those parties, Charlie. So Alice now is the one who makes a choice. So Charlie and Debbie are not making choices. Alice is making a choice. If she makes choice 1, so if X equals 1, then she simply opens a window in the lab and asks Charlie, what did you see? And then he will report his answer, and Alice will take that to be her answer in the experiment as well. Okay, so that's how she gets her observation. In that case, it's simply, as in the original Wigner's friend, she simply asked the friend what he saw. Okay, but for this experiment, we need, in the other cases, okay, so if X is not equal to 1, if Alice makes a different choice, then she does something very different. What she does is use her superpowers to reverse time in Charlie's lab. Okay, so everything in Charlie's lab is reversed for a second, say, and that means that Charlie becomes, that undoes the measurement. Okay, and so Charlie now becomes unentangled with the quantum particle again. And at that point, Alice simply throws Charlie away, takes the quantum particle and makes her own measurement on that in whichever basis she chooses. Yeah. Okay, so how does this one pan out? So now, as I said, so there's no assumption here of hidden variables, which I don't know if I mentioned before, but that was what the lambdas are typically called that exists on the space-like hypersurface. So here we're not assuming anything like that. We're not assuming anything in the world is really exists except for observations, which seems to be the absolute minimalist type of ontology that you could have. Okay, so we are still assuming that the absoluteness of observation is true. So, and that means assuming that the observations that Charlie and Debbie made are real events, okay? Even if they can be undone later, when they happened, they were real events. That's the assumption here. And so, yes, so the absoluteness of observations means that there is a joint probability distribution over those 4 things, A, B, C, D, they're all real events. And also that in the case where Alice measures with setting choice 1, that when she opens the box and asks Charlie what he saw, that the result she get is indeed just what Charlie saw. Okay, that's a by construction for the experiment, and the same with Bob and Debbie. Okay, so that's the implications of that assumption. The implications of local action are fairly much the same as before. This is where relativity, causation, speed of light comes into it and puts limits on what these constraints could be. So these are not the same constraints as as in a Bell experiment. So we term a new phrase for these. We call the conjunction of these metaphysical assumptions local friendliness. Okay, so for this, a combined metaphysical assumption here. And so it's not obvious that this assumption, because it's strictly weaker than in Bell's theorem, as I said, it's not deterministic hidden variables. Nothing here indicates that things are determined. The only things which are where we definitely have a correlation between things is in the case where Alice opens the box or Bob opens the box, but in other cases that's not the case. So it's not obvious that this is going to give the same constraints on correlations as the local hidden variable assumption. And indeed, it actually doesn't. Okay, the assumptions which we've got here, as I'll get to, are different. Nevertheless, they can still be violated. Okay, so this metaphysical assumption of local friendliness, this conjunction of those two assumptions, implies constraints on the results that everybody can agree on. The probability or the correlations between Alice and Bob's results given their settings. And we don't actually even need superpowers to exist in the sense of being able to do everything absolutely perfectly. They basically just have to be good enough. So these time reversal operations have to be good enough so that the probabilities or the correlations that we see here when Alice and Bob undo their or reverse time in Charlie's and Debbie's lab is approximately the same as if there had been no measurements by Charlie and Debbie in the first place. So it doesn't have to be exact. It just has to be in much the same way as Bell's theorem. It just has to be good enough to violate a certain inequality. And so, as I said, what we have here is a new theorem of experimental metaphysics. Okay, so as I said, so this is not the same as the Bell's assumption. It's not the same as local predetermination or local hidden variables. It is actually a strictly weaker assumption, which means that you can have correlations that violate Bell's assumptions, but don't violate the local friendliness assumptions. If you go to an experiment with more than two settings. And so that's to demonstrate this, that's what we did in the lab. So yes, so just to tell you, we're going on to the experiment. So this is the experimental setup. Okay, so there is it's a photonic experiment. So here is the source of entangled particles. They go into, this is Alice's side and this is Bob's side. Now, the friends, of course, are not macroscopic conscious friends, at least not by what most the criteria that most people would use for those terms. What the friends are just another degree of freedom of the same photons. So the photons are entangled in polarization, and what we mean by Charlie making a measurement is Charlie is going to be the path of that photon. So Charlie making a measurement of the polarization of the photon is simply using some evolution in the lab to make a perfect correlation, more or less perfect correlation, between the polarization of the photon and its path. And that's a thing called a polarizing beam displacer, which we have here. Right, so then Alice makes a choice. If Alice wants to simply know what Charlie saw, then she puts a mirror here, and if Charlie is in one state, so in this beam, then Alice will find out because Charlie will enter this detector here, and if the other case, then Charlie would enter this detector here, and that's how Alice finds out what the polarization was in this particular basis. On the other hand, if she wants to measure do a different measurement, measure in a different basis, so to speak, then what she has to do is reverse time in Charlie's lab. And that's relatively easy. Well, that's a theorist's perspective. It's obviously a delicate experiment. One can put various optical elements which reverse this path and produce at the end the photon with no correlation with its path. So the path of the photon carries no information about its polarization anymore. These things have become disentangled again. And now Alice can just take the photon and measure its polarization in any way she wants. Okay, so that's the other choice. By not putting in a mirror here, she can implement the other choices. And the same thing is happening on Bob's side there. Pardon me. Okay, and so the results show indeed a violation of the new types of inequality which we derived. So that's what this brown one here is. We have new inequalities, which are not Bell inequalities. What we also see in this graph is the fact that we can have local friendliness inequalities. So that's this green one is another type of local friendliness results. So sorry, in this case, anything bigger than 0 indicates a violation. They've all been normalized in this way. And so the idea, and what we have here is a parameter in the state, which is varied, which is basically how mixed it is. So as this, how pure it is. So as this gets less and less, it gets harder and harder to violate the inequalities until over here, there's no violation of any of them. Whereas when they're very pure, they are all violated. And the point is that as one gets less and less pure, the local friendliness correlations all cease to be violated before Bell. So the Bell violation still happens, just demonstrating that there is a difference between these types of correlations. Okay, right. I think at this point, even though I've explained the experiment, I think a lot of people are still potentially confused. So you might be asking, hang on, what exactly was the friend in the experiment? And so just to reiterate, in our experiment, the friend was a qubit, by which I mean a binary degree of freedom, which is the path, because there are only two, it only has two possible paths, of a single quantum particle, a photon. So you can ask, can a qubit be your friend? And also, didn't you say that you needed superpowers to do this experiment? Well, obviously, I would say a qubit is not a real macroscopic friend, as I said. So, and that's why we can do this experiment without superpowers, just with normal experimental quantum optics powers. So we're clear in our paper that we're not doing the experiment associated with this theorem. We're doing a microscopic proof of principle version of this experiment. So some of you might be aware that there was another paper last year related to Bruckner's original paper. And in that paper, their observers claim that their qubit is an observer or is Wigner's friend. And yes, that's true. Okay, I see that I'm, I don't know whether it makes sense to pause at this point because I know we're actually getting close to the end. So maybe Ephraim can make a call about whether it actually makes sense to pause at this point or just to churn onwards towards the end and then have questions.
Yeah, I think since you should try to finish up in not too much more than 6 minutes, maybe we can just hold the questions until the end.
Okay, all right. So hopefully people stuck with me despite my
most happy.
Okay. Oh yeah, okay. At least they've been counted. Okay, so so as I said, that was a toy experiment. What I'm interested in personally is what would a real experiment look like? Okay, what would it mean to really test the local friendliness assumption? What would be a real convincing friend or observation? So could it be encoding information in a simple quantum system? I'm going to say now, no, I don't think so. Well, what about a sufficiently large or complex quantum system? Well, maybe, but there are many different ways of talking about largeness or complexity, and it's not clear in any of these what a particular threshold would be meaningful. So a bit problematic. What about, like many of you might be thinking, well, surely an observation, we know what an observation is. Bohr told us, well, actually Wheeler told us, pretending to be Bohr, that an observation was an irreversible act of amplification. That seems pretty reasonable, but obviously if that's what an observation is, then we simply cannot do the experiment we want to do here, because the whole thing is that the experiment requires the reversal of the observation. Okay. So what are we left with? Well, I'm going to say, if we go back to Bruckner's paper, he talked about an immediate experience by a sentient observer and as being essentially what an observation is. And I think ultimately that is the best alternative. Okay, but if that's going to be the case, how are we going to reverse time for a sentient observer. That seems absurd. How could we actually do this? Well, I'm going to argue that it's not absurd if we think of that sentient observer as being realized on an enormous fault-tolerant quantum computer. And so this is where it comes in of what we need. But let's say we had this, and I'll say more, that how would we convince that such a device was actually a sentient being? And I would say you would have to behave like a human. We could interact with it. It would, in other words, have to be capable of being a friend, okay, in a genuine sense. So this is why I'm not just, it's the picture I had before. Yeah, as I said, is a genuine representation, if you like, of what I think would be necessary for a true experiment would be to have a quantum computer capable of running an artificial intelligence algorithm for which we could form a genuine friendship, okay? For which we could be convinced that there was a party in there, so to speak, whose observations we would treat on the same level as our own. Okay, so I guess I'm going to skip through this. So yeah, essentially, yeah, one of the things which we found out in our work is you don't actually need two friends, you only need one friend. So that's good. You only need one ginormous quantum computer, not two of them. So that will please the funding agencies. But other than that, essentially things go as before. So we have a qubit, which is observed by Charlie in the sense that just incorporated into Charlie, this quantum computer's matrix. And then Alice can either ask Charlie what he saw or not, reverse time for Charlie, throw Charlie away, make her own measurement on the qubit. Okay, I think I'll skip this slide about how this could practically be done. Obviously, there are enormous challenges to think about doing this. But what do we get to in the end? What sort of theorem do we get? So the point here is to get to a theorem without assuming this sort of a ridiculous thing of superpowers. In other words, what reasonable experimental assumptions that would enable us to get a contradiction with a real friend. Okay, and so again, I've done things in yet another way. But the idea here is to put in minimal assumptions which are needed for me to actually treat the friend's observations at the same level as mine. So we have to, so let's go with, so start with number 2, I'm calling ego absoluteness. It's just the idea that my thoughts, I will treat at least my thoughts as being absolutely real. If I were asked to communicate them to another party, I could do that, then I'm going to say that those are absolutely real thoughts. And so friendliness, now I've got an explicit assumption of friendliness, is that if I find other parties to be cognitively equal to me, I can interact with them, and they seem roughly the same as me in their thought processes, then I will give their thoughts the same ontological status as mine. Okay. And you might think that's basically all, but they're really strictly to apply concepts like local action, which is the same as it always was. We really actually need another assumption, which these thoughts, which I'm talking about, do correspond to things in the world. So that's an assumption of physicalism, that a thought has an associated physical process in the brain or wherever else, you know, in the central processing unit or whatever of the party whose thought it is. Okay, so those are the metaphysical assumptions. The actual experimental assumptions that we need to be able to produce human-level artificial intelligence, which still has not been demonstrated, but probably will come, although different opinions about this, before, but that's arguable. No, I think very likely before universal quantum computing at the sort of scale that would be necessary for an experiment like this, which is an absolutely vast scale, much, much bigger than necessary for a useful quantum computer as usually defined. But the point is that these are not anymore ridiculous fantasy assumptions. These are things that we could really imagine doing if technology continues to advance for decades in the way that it has been doing. And so that's really my long-term vision, is that there will be a real experiment somewhere down the track that could be done to test assumptions like these. And I think it would be a very interesting experiment because, and I guess I just don't have time to go through this, but it has real implications for a whole lot of interpretations of quantum theory. And maybe what I'll emphasize most is that I think the sort of no interpretation, which arguably most physicists have, simply does not hold up in the face of this theorem. So there are none of the assumptions in the theorem that would be obviously rejected by a sort of, oh, quantum theory needs no interpretation. It's just obvious what it means. No, that just doesn't stack up anymore. Like arguably in Bell's theorem, you just say, oh, well, the predetermination, obviously I reject that because quantum theory is not a deterministic theory. So that's obviously wrong. And that's the end of the matter. Okay. When we get to this theorem, no, I think if you ask, do you believe in this, local action, physicalism, ego absolutism, friendliness, there's no particular reason to reject any one of those unless you've actually thought about quantum interpretations. And so I think that it would really force, it would force the matter, force people to recognize that, no, we can't talk about quantum theory without interpretations. But still leaving many options as to, which assumption gets rejected, including, interestingly, perhaps some of the experimental assumptions. So perhaps human level artificial intelligence is just not possible for a quantum reason, or perhaps universal quantum computing is just not possible for a quantum interpretation or quantum theory reason, which I think would be obviously the most interesting outcomes if one tried doing an experiment like this. Okay, so take-home messages. The idea of experimental metaphysics is that non-testable metaphysical assumptions can have falsifiable empirical consequences in conjunction. Okay, and in the case of Bell, we can actually say that these are falsified experimental consequences. And so what I've been telling you about is the idea that continued advances in artificial intelligence and quantum computing, and also quantum communications, I didn't really mention, will open a new frontier in experimental metaphysics, but down the track. So specifically, we could rule out the conjunction of these metaphysical assumptions, which I've listed below, and although, as I said, we performed an experiment, which is the first step, I think, in the direction of a real experiment that would test these assumptions. Thank you for your attention.